Classifications of matter. Again, this is more review from Gen Chem. We've even mentioned it earlier in this chapter, but let's do it again with a little bit more feeling. Talking about states of matter. So we're going in between the solid to liquid in the gas phase, and also back again. There and back again. But let's be very, very clear that changes in state, solid, liquid, and gas, involve altering intermolecular forces, not altering actual chemical bonds. Right? We're not changing bonds. And so maybe when you were little and you'd see water boil on the stove, you might think that the little bubbles that were coming out were hydrogen gas or oxygen gas. That is not the case. There's a little H2O gas bubbles, right? It's actually steam. And that's why when you heat water on a stove, you'll actually see steam. That's what that is. It's steam. It's water in the gas phase. You can produce hydrogen bubbles and oxygen bubbles if you run an electric current through water. It's called electrolysis, right? But that's not a change in state. That's going to be an actual reaction, right? So when we talk about simply moving from the solid to liquid to gas and back again, we are only looking at IMFs, intermolecular forces, not intra, meaning the things inside the H2O. We're not looking at those, right? Those are the bonds, the chemical bonds. We're not changing those. So in the solid state, items are very, very rigid. They have a definite shape and volume. You've probably heard that before for sure. Definite shape, definite volume. Molecules are very, very, very close together. And they're so close together, they're actually not moved. They're actually fixed in a particular location. Not to say that they're not moving, because remember the KMT, right? Kinetic molecular theory. Things are always moving. Unless you're at absolute zero, in which case things aren't moving. But these molecules are very, very close together because they're not at absolute zero. They are moving, but if they're in around fixed points, they vibrate. They have vibrational motion, vibrational energy around fixed points. But because they're so close together, right? So connected to this idea, they're virtually incompressible. You can't really compress them any more than they already are. Because they're so close together. All of these IMFs have got them clumped down close to one another so much that they really can't get any closer. In the liquid state, we still have a definite volume, but the liquid is going to take on the shape of the container, right? And so we're losing the definite shape here from the solid, but we're keeping the definite volume. So we don't have a definite shape, we have an indefinite shape. So the liquid's going to take on the shape of whatever it's in. Now again, KMT, we're always moving. Think about your natural exposure to water, right? So as you go from the solid liquid to gas, what's the temperature doing? It's going up, right? You increase the temperature to go from ice to liquid water to steam. So as the temperature is going up, again, according to the KMT, about things always moving, what does that say about the movement? It means that there's more movement when you go from the solid to liquid state. So these molecules, they have the same vibrational movement, the same vibrational energy that they had, right? So they still vibrate, but they also have rotational and translational motion. So rotational, meaning that they can rotate along their own axis. Up here in the solid state, they couldn't even spin in place. They could only vibrate. In the liquid state, they can actually spin in place along any of their axes. Translational, that simply means to move, to translocate, to change your location. And so you're moving, right? They're moving within the volume, right? It's still definite volume. They're moving within the volume. And what that looks like with liquid molecules is individually they are sliding past one another. So they're still very close, right? They're still very close together. This is still very true. They're very close together. A little bit further apart than they are in the solid state, but they're still very, very close to one another. So in order to change location, right, translational motion, they're going to be essentially be sliding past one another, right? Sliding past one another. Then we increase the temperature a little bit more. We get to the gas phase. In the gas phase, we don't have a lot of definite anything anymore. We have no definite volume, and it's still going to take the shape of the container, which means no definite shape as well. So no definite volume, no definite shape. That is a gas. So now, since we're increasing the temperature, therefore we're increasing the kinetic energy, which means the energy of movement, right? We're increasing the movement. So we still vibrate, okay? Boom, boom. We still rotate, boom, boom. We still translate, boom, boom. But now we're going to add that movement. The movement of an individual molecule is going to be independent of the movement of other molecules around it. And one of the reasons that is very true is because there's not going to be a lot around it. These gas particles are going to be very, very far apart from one another. They're going to expand. They're going to move away from each other on the realm of 2,000 diameters apart. Right? They will spread out. So if a molecule is, if I'm going to draw a gas particle looking like this, which is not super accurate. So think about the diameter of this molecule. It's about boop, boop. It's about that wide. 2,000 of these, right? If this is how large the gas particle is, 2,000 of these is how far away its closest neighbor is going to be. So these things expand significantly. But because of this significant expansion, they're going to be highly compressible. Right? That's one of the key characteristics of gases that we harped on in Gen Chem. Within this idea of gas, we have the term vapor. And I used to think, until not all that long ago, I mean, relatively speaking, that vapor and gas were interchangeable terms. They are not. Right? Vapor is a term that we can use as a state, if we wanted to get a little bit more descriptive. That says that the gas phase is of a particular substance, so it's relative to the substance that is normally a solid or liquid at room temperature. For example, water. Right? Water is at room temperature is a liquid. And so if there is something that's been vaporized, right, it's not normally a gas at room temperature. For example, another example, iodine is a solid, but it sublimates, meaning it goes straight from the solid state to the gaseous state without ever being a liquid. Another example of things that sublimate, dry ice, right? If you ever heard of dry ice, the reason it's called dry ice is because it's cold, it's solid, right? So ice, right? It's solid and it's cold. And it's dry because you'll only see that kind of like smoke coming off of it. It never turns into a liquid. There's never a pool of anything to clean up. So it's a dry ice because it sublimates or sublimes. The idea of a fluid, right? Fluid refers to being able to flow. I almost wrote flow again down here, but a fluid is anything that can flow. Things that can flow are gases and liquids. There are some other things that can flow, but they kind of like stretch our definition of what it means to be a fluid. And in fact, they're in other areas of science. We're not going to focus on those too much. So as we go forward, and we will revisit the KMT in this course, and we'll try to get a little bit more in depth with it. But we're going to have to keep these ideas in mind as we go. Solid, liquid, gas. There's always a certain amount of movement, right? According to the KMT, they're always moving. We go from very, very close together and only vibrating around fixed points, not compressible. We add a little bit of kinetic energy, so we get more motion. So we're still vibrating, but now we're rotating and translating and flowing, right? Sliding past one another, we can flow now. We're getting the tiniest bit further apart from one another, so we're slightly compressible. And then a gas is going to have even more kinetic energy, so we're going to be able to vibrate, rotate, translate, and all of those motions are going to be independent of the other gas particles around them.